Good afternoon, everyone. We will start in 1 to 2 minutes time. Alright, good afternoon, everyone. And today's tutorial is going to be focused on the questions, especially that came in from the students in particular, that we recorded in our first 3 lectures. Now, there were 4 particular questions that were recorded, and just to highlight these, there's going to be the difference between a character array and a string, especially considering when we are outputting them to the console screen. Overloaded functions, recursion examples. So basically, first to observe how actually does the recursion operate with respect to how does it unfold with the multiple function calls, as well as with the concept of memoization in the recursion to see how do we keep track of a temporary memory register inside there during our recursion to get our correct output. And the last thing we'll be discussing will be black box testing, and the reason why we are using command line parameters black box testing, along with one of the functions that the students were required to research, which was the A to I function or the A to F function. And we're going to see why is this particular functionality with the black box test, when we reach this point, why it is quite important for us to use this function in particular. So the first thing we're going to do here, and you can basically see that I had Visual Studio up and running in the background, is that we're going to be discussing the difference between a character array and a string here for outputting towards the console string. So a character array is basically like we'll say char, and then we put open colors square brackets to indicate that's going to be an array, and then we can just give it a name. So let's say like name, and then we can put whatever characters we want in between the double quotation marks here, for it to be allocated as of such. Oh no, I'm doing this wrong side, sorry, wrong syntax. So char, name, and then we put the square brackets next to the name for our character array here. Right, the previous instance where I just looked at here was for another programming language, so you'll have to excuse me for a bit. So, right, for C++, we'll say char first to indicate that's the character data type. Then we give a variable a name, which in this case is obviously name. And then we put the square brackets next to it to indicate that's going to be an array. And we can immediately allocate this array here to some sort of characters. Now, the reason why this works here is that when we initialize our name character array here, even though we didn't put a number here to specify the size of the array, on the initialization, because we're storing these characters immediately, the compiler will automatically allocate the size of that character array for us into our name array here. And because we do this in particular, if we go stdcout and then we put name here. If we build our program and then start without debugging, you can see here that we get our character array being outputted towards the screen. So this is a nice way of how character arrays can be used for output regardless. But please note, the only reason why this is working in this particular case is because upon initialization of the character array, we specified what we wanted in it immediately. So let's close this off, and let's show you what happens when we don't do this. So let's say we have character array name here, right? And immediately we can see that we have an incomplete type. And this being that we need to specify what is going to be the size of our array. So let's say ECNG 2000 was 8 characters, so let's put 8 here. And then if we try to put name here is equal to ECNG 2007, we can see that it doesn't agree with us. It's like this needs to be a modifiable literal value. And what this means is that once we try to allocate something to our name character array here, if we didn't do it upon the initialization step above, which is here, we're now going to have to do this one character at a time in order for us to store characters inside there. So, for example, I have to say name 0 equal E, and note I'm using single quotations for the characters. Double quotations is a combination of characters. That'll have to be like name 1 here equal to C, and then name 2 is equal to N, and name 3 here is equal to C. But I could just put it in for 2007 and whatnot, but you're basically get the idea at this point. So let's rebuild this, and then let's start without debugging. And what you can see here is that because we didn't fill the array, we're going to have some garbage here. So this is what you have to look out for in particular when you're using character arrays. If you use the character array immediately upon initialization and you allocate your characters into it, you don't get this problem. But if you use the character array afterwards from when you declare it, you're going to encounter this problem if you don't fill up the entire character array. And just to illustrate this, let's go. Name 4 equal to 2. Name 5 equal to 0. 6 is equal to 0. And name 7 here is equal to 7. And let's see if we still get some garbage once we build our solution here. And stop without debugging. And we can see here that we still get some garbage regardless. So this is the danger of using character arrays in particular. There's going to be some garbage if you don't immediately initialize it upon its creation. If you declare it and then you want to use it afterwards, you want to run into this particular problem here. If we don't want these garbage character arrays here, we can't use the cout name as is, because name here is what's responsible for storing all those garbage characters we just saw on screen. So if we want to safely output this, we're going to have to use a for loop here. So we'll have to go for int I equals 0, I less than 8, I plus plus. Then we have to put cout name I and leave it as is like that, because we don't want to end the line here, because then we'll get the entire thing appearing vertical. We want everything to appear horizontal on one line. So let's build and stop without debugging. And we can see here we get a nice ECNG 2007. But this is just like a sort of trickery that we just did here to make sure that we don't print the garbage characters that are being stored afterwards in that name character array as of such. So this is why you need to be very careful about using character arrays when it comes to C++. And in particular, when you move on to microprocessing systems where you won't have access to your string library, you will end up using character arrays in particular. So you need to be very careful when you're using them because of this kind of garbage that the compiler will be allocating towards it and so forth. Now, if you're using a string, you just say sc string name and then put ECNG 2007 here. Because basically a string is just a collection of characters, so it's like a fancified character array that is more clean and a lot more simpler to use. Then we can just say std cout name and line here. And we can build our solution and then stop without debugging. And we can get the same output as required. Similarly, because like I said, a string is basically a character array, if we wanted just to output one of the characters, so let's say name 0, and we build back here, and we stop without debugging, you see here that we just only get a single character here, which is just going to be E. So we can access individual characters here in particular. Let's say if I wanted G, G is the 4th character, and an array always starts at 0 in C++, so that's going to be 4 minus 1, so that's 3. And if I build here, and I'm going to stop without debugging, you can see here that I get my G character as required. Alright, so that's basically the key difference between a character array and a string. That with character arrays, even though they came before strings, you have to be very careful about how you use them because you will get some sort of unexpected behavior. And we saw this unexpected behavior when we tried to output the character array and we start seeing a whole set of garbage characters afterwards what we wanted. To prevent this, we could have used a for loop and output a character one at a time, but that still doesn't solve the problem that the garbage characters are still hiding in the background there. It's just a sort of trickery that we do just to make sure that we don't get the garbage characters showing on our output screen. Strings came along after character arrays to like resolve all these problems and to give a lot more ease of use regards to using characters. And it's a lot nicer to use the string library here. But when you go down to microprocessing systems, you won't always have access to that string library due to limited space. So you will end up being forced to use character arrays regardless of the situation. And it's important always to know how to go about doing the two as of such. Yes, you can add two of them together, but it's going to be like if you want to have a character array and another character array, and then you're trying to add two, or if you have a string and you're trying to add two. So with strings is easier to do. So like we can say std string class. No, I can't use class. Class is a keyword. So name2 is equal to tutorial, and then I can put like name plus name2 here. Oh, no, I have no spaces here, so I'm just going to put a space right here to make it look nicer. And in this case, it won't work because I'm doing it in the cout. So if I wanted to do it here in the cout, I'm going to have to use the cout operators here for it to show up properly. Oh, I'm missing this. Right. Okay, nice. Oops, I still may be able to add it here. Yes, I can add it here. Okay, nice. It's just because I was missing that semicolon. So let's build and stop without debugging. And we can see here that we get our two strings being added together. So the addition symbol here, or the addition operator, it basically joins the two strings together, or another fancy way of saying this is that it concatenates the two strings together. Similarly, if I didn't want to use the addition here, and I put the two less than brackets here for our cout, which is basically like if we're trying to append two different outputs in our cout here, we're going to get the same result as required. I could debug, stop without debugging, and you can see that I get the same thing as before. With character arrays, it's going to be a little bit different. So I'm going to show you why it's going to be a little bit different with character arrays. So let's say char name equals ENG 2007, char name 2, go to tutorial. Now, I might get away with this, but we'll see. Alright, see, so it won't work here because when we try to add two character arrays together, it's going to be like, wow, it doesn't know how to do this. So the string library actually has what we refer to here as an overloaded operator, where it knows to use the add operation here to join the two strings together. With character arrays, this isn't possible. So if we want to join the two, we're going to have to use the cout operators here, being the two less than signs, in order to get those two to show up properly. Build solution. And if we start our debugging, we can get the two of them showing up here properly as required. Alright, so any particular questions between the differences of character arrays and strings at this point in time? Right, doesn't seem like we have any questions regarding this. So we'll go on to our next topic, which is going to be overloaded functions. Now, overloaded functions is like when we have a function. Oh wait, we do have a question. I'm getting to the argc and the argv in a little bit. That's when we get to the black box testing. So I'll explain what those mean in a little bit. So just hold on a little bit. Once I get to that, I'll explain what it means again. For this particular class, there may be an instance where you may end up having to use a character array, and it's going to be because of a memory limitation. And that could be because of particular software that you're using, or if you're required to develop your software for a particular piece of hardware, you have to end up using character arrays instead of strings, mainly because the string library is not going to fit due to that memory limitation. And the reason why I'm showing you this in particular is that next semester, when you go into Introduction to Microprocessors, or Microprocessors 1 in that particular case, you're going to end up using character arrays. You can't use strings. And that's really because the microprocessor doesn't have enough memory for you to use strings. So you have to know how to use the character arrays regardless whatsoever. So when you're using character arrays in particular, you have to use the cout operators. Like if I try to put this add operator like we did for strings, it doesn't know what this add operator is supposed to do. This add operator works because in the string library, it redefines its add operator here to know to join two strings together. But when using character arrays, you don't have this functionality. So you have to end up using the cout operator here to join these two character arrays together for your output. Alright, so as usual, if there are any questions, feel free to interrupt and I'll address them accordingly as of such. So we're going to be moving along to overloaded functions at this point. So an overloaded function is basically where we have two functions that have the same name, but they can be doing different operations altogether. And the way that we distinguish between the two of them is that they're going to have different input requirements towards these functions. So let me just clean this up here inside my main function for the time being. And let's do a simple overloaded function here. So let's say int add is int a, int b. And then we just want to return a plus b here. And then similarly, we can have int add here, same function name. Then we can have int a, int b, int c. Then we can have return A plus B plus C. And then we can have add 2, 3. And I'm going to have to output this for you guys to see what it is. Similarly, I can have add 3, 4. So let's build our solution here. And then let's start with our debugging. I can see here that we have, when we add 2 and 3 here, we get 5. And similarly, when we add 2, 3, and 4 here, we get 9. Now, let's take a closer look at how this actually runs. So, I want to put a breakpoint here for our first add function here, where we just add in 2 integers, and another breakpoint here for our next add function, where we add the 3 integers together. And let's step through our program here, see what happens. So, we're going to go debug and step over. And you can see that we enter in debugging here. And then I'm going to start running here. And at this point, I want to step into to see what happens. So I'm going to go step into. And step into will let me jump into the add function that we called here in our cout statement. So once I'm inside here, you can see that the arrow points that we're inside or we're about to execute this function. And we know that from this function call here with the 2 integers, it knows to go to this function because this function only has 2 integers as input. So then I could go step over again, which is F10. And we can see here that A and B in our watch window have been allocated values of 2 and 3 that were passed from the main function. And I can step over again and step over one more time, and we come back here. And we see that the add function here in our watch window returns the value of 5, which is required. I can then step over one more time and to see, okay, we're going to be calling the next instance of our add function where we add in 3 integers. And I can step into, which is F11, to make sure that I do go into that function that's being called here. And we can see that instead of calling this function, the compiler knows that, okay, we're adding 3 integers, so we want this instance of the add function instead. So it goes to this function instead. And then we can just step over, see that 2, 3, and 4 from our main function is passed as A, B, and C. Step over one more time. We hit the end of the function and step over, and we can see that the add function here returns the 9 value as required. Step over one more time. If we pull our console window to the side here, we can see we have 5 and 9 on our output screen. And we can just continue at this point, and our program will just finish as required. So overloaded functions is a very nice way of having 2 functions with the same name, but they operate completely different from one another. And that's because they have different inputs for their requirements here. Now, similarly, I can add a third overloaded function here and put int add, not int add, sorry, double add, int a, b. But this is going to be a problem. Actually, no, it doesn't be a problem. Okay, my bad. This wouldn't be a problem. So we can put that we want to return a plus b here. And remember, this is going to be a double that we're returning here because we're now adding an integer and a double, which is basically a decimal value. So let's do this here. Cout add 2 and 3.5. And let's see what happens when we do this. So I want to breakpoint to this part here. And instead of stepping over, I'm going to use the breakpoint to stop our program here. So I'm just going to go debug and start debugging. So our program will automatically execute up to this point here, which you can see by the yellow arrow. And then I'm going to step into it to see which one of these functions that is being called. So I'm going to step into which is F11. And we can see here that we automatically know that the compiler has resolved this first, because it means, okay, the first input here is an integer, but the second input here is a double. So we need to go into this addition function instead of the other two that were defined from before. And I can step over that, and we can see that A and B got the values as required from the main function. And then I can step over to get back to our main function here, and we can see that the add function, in this particular case, or double add, returns the correct value as required. And I can just hit continue and finish executing our program. So that's how overloaded functions work. It's basically that you have functions with the same name, but you can change the amount of inputs as required. You can use different types of inputs, and in some cases you can actually change what do you want to output or return from the function, and the compiler automatically resolves this by knowing, okay, we have these particular inputs and we want to return this particular output, so we know which one to use in particular regarding that. Any particular questions regarding overloaded functions at this point in time? Oh, okay, alright, I understand what you're asking now. Right, so the reason I got away with that is because, remember, I initialized the character arrays immediately upon their creation. If I did not do that, I would have to end up using 2 for loops in order to get the characters to output on the screen as required. So, like, I'm just going to write some scratch code here underneath so you can see what I end up doing. So, like, it would be like if I had char name, and then I said, like, I wanted 4 characters here, and then I put name 0 equal to whatever, like E, and I had the allocations and so forth, and then I had like char name 2, 4 characters here. I have name 2 equal to name 2 0 here is equal to T or something like that. If I wanted to output those in that particular instance, I would have to go for int I equals 0, I less than 4, I plus plus. And then I have to put std cout name I here. Then I had to put it, then I'll have to repeat this for loop again. So I'll end up copying it. And instead of name I here, I'll be putting name 2i altogether. So the reason why I got away with that in particular is because, remember, I initialized the character arrays up front once I created them. But if I didn't do that, I would have to end up using these 4 loops here altogether. If I did not initialize the character arrays and I didn't use the for loops, and I end up using the cout function, I would have gotten all those garbage characters that you just now saw when we just outputted one of those character arrays altogether. So you just have to be a little bit careful when you're using them in particular, but either way is fine. If you do initialize your character arrays upon creation, you can get away using the cout functionality as is, without having to use the for loop. But if you don't initialize your character arrays upon creation, and then you allocate values into it afterwards, you're going to have to use independent for loops here to output each character array at a time. Alright, so hopefully that resolves the question that you were asking. Yes, a dynamic function can be created, but that's regards to when you start using classes in particular. And that's where I was explaining that you have to use the new operator and whatnot and so forth. So we will get a lot more experience using that in further tutorials and further lecture sessions when I go into more detail about creating dynamic functions in particular. Alright, any further questions at this point in time regarding overloaded functions? If you want to do a little bit of research on the dynamic functions, what you want to look for is the virtual keyword C++. So that gives you an idea of how you can actually go about creating a dynamic function. We're also going to see later on how we can actually dynamically create and destroy memory later on in regards to variables. But with functions, if you really want to do a little bit of research behind it and read up how it works, you're looking at virtual functions in C++. I'll type it out here for you. So you say like if we had int A and int B here, no, it won't work because you want to see here that the compiler is going to complain and be like, cannot overload functions distinguished by return type alone. The parameters, the input parameters must be different in some form or fashion, be it that there's more or less input parameters, or there are different data types for your input parameters. So if I had int A and int B here, it's not going to work. The compiler will refuse to compile altogether. That's why I had int A and double B here in particular. Alright, doesn't look like we have any further questions regarding overloaded functions. Alright, so let's get on to our third topic, which is going to be the recursion example with the breakpoint and watch windows. So let's clean up our main function here. And let's actually write the second recursion function that we had in our slides. It's going to be int sum of squares, int A, int B. And inside here, we had if A is more than B, we had to return results. Now, at this point, the compiler is going to be like, okay, what's result? Because we didn't define this inside the function. So we're going to have to put int result A is equal to 0. And then for a recursive step, remember this here was our base case from our lecture slides. We'll have result here is equal to plus equal A by A. And then we need to return sum of squares A plus 1, comma B. Now, I'm writing this without the add result here because I want you guys to see what happens when we don't add the results in our return statement here. And this is going to be because we have int result A equals to 0 at the start of our function. Let's see what happens when we do this. So let's call sum of squares here, and let's say 2 to 4. And we're going to run this first without debugging and see what result we're going to get. And we see that we get a result of 0. And it's like, okay, that's the wrong result. We're not supposed to get that. We're supposed to get 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, which is 16. 16 plus 9 plus 4, which is 16 plus 13. Get 29 if I'm correct. That is correct. 25, 29, yep. Get 29. So why did we get a result of 0? So let's actually start breakpoint in here to see what actually did happen. So if we start with debugging and we start observing what happens for each instance that we go about doing this, you can see here that 2 and 4 has been passed to A and B as required from our main function. And A is still less than B. The result here stores 4, which is the result of 2 squared from A. Alright, so let's step into here because we want to go back into our function. And we want to step over. See that int result here is at 0. This line hasn't executed as yet. So we see result here changes to a value of 0. But A here is now a value of 3 because we have A plus 1. We do this check here to see if A is more than B, and that's not true. So we ignore that, and we go to the else part here. And we have result is plus equal to A by A. We execute that line by stepping over it. And we see result here stores a value of 9. But it did not keep track of our previous value. We have plus equal here, meaning that we need to make sure that the result is stored from the previous recursion, but it didn't do it. And then similarly, if we watch this again, let's step into our return sum of squares here, and step over again. You see A here has changed to 4 because of that A plus 1. We do our check again, it's not more than B. We go here, we run our result, and we see result has 16, but it's not keeping track of the previous recursions. So we lost that 4, we lost that 9, which was a result of 2 squared and 3 squared. And we're going to see here that we're also going to lose a result of 16 as required for the recursion. So if we step into this function one more time, and we reach result is equal to 0, and we actually have A here being more than B, and we return results, we see results has a value of 0 that is stored here. And that's what it's going to return. It's just going to return 0 for each one of those recursions. So that's why we end up getting a value of 0 here, because we didn't have any memoization or any memory to store our recursion values altogether. So that's why we need to make sure that when we're doing recursion and we need to keep track of some running variable inside our recursion, when we have our recursive step here, we need to make sure that we add that memoization or that temporary memory into our return statement so that way it knows to keep track of that result altogether. So I'm just going to breakpoint here because we no longer care about when it's going to be more than B. We know that it's going to do that. Actually, no. For illustration, I'm going to breakpoint here as well to show you guys. So let's see what happens when we have this add result here in our recursive step. So observe how does memoization takes place and how it actually keeps a temporary memory register here, or a temporary memory variable, to store the values from previous recursions. Then we go start, and we start with debugging. Alright, so we reach here, return sum of squares A plus 1, comma B plus results. So A is 2 here, B is 4, result is stored in a value of 4. And let's step into our function here we are calling. So we actually are back at the start of our function here. I'm going to be like, okay, 3, 4, result here stores 0. A is not more than B. We reach here. Our result stores is 9. Okay, that's fine. We're still seeing the same behavior that we had from before, where result is not tracking this. But wait until the end and let's see what happens when we compound our result. So let's step into our function again. And we keep on going. A is still not more than B. A here is 4. Result stores a value of 16. Let's step into our function one more time. At this point, A is more than B. Result here is 0 because we initialized it to 0. And now we're going to be returning our results. So we reach the end of our function here because we're going to return it. And let's see what happens as we step into it. So we have the result of 16 here being stored. The sum of squares returns 0 for the first iteration. And this is because we're stepping back into our function, not stepping over it. So that will be the first recursion that actually happened here. For our second recursion, sum of squares returns 16, and result is 9. And this is because the result here acts as a memoization or a temporary memory variable to keep track of that result for every recursion step that we just loaded. So in this particular case, when we step into it again, and we reach the end, we still here see that result here is 9, but when we step into again, we see that 16 added together because of that return, and we get 25. And then for our next recursion, the result here was 4, which was 2 squared. And we get back to our main function because all the recursion steps have been completed, and sum of squares returned here is 29, which is our correct value as required. And just to show the result here, we have 29 on our console screen. So that's how you visually observe how recursion works. So what recursion basically did here is that it went I'm just gonna give you guys a little comment here. Sum of squares 2, 4. Then it went sum of squares 3, 4. And sum of squares 4, 4. So that's how we saw it operating to begin with. But for it to go back when it's returning here to get our results, highlight this a little bit. Recursion starts this for all function n. Function call ends. And then when it's time for all the function calls to end, it will go in the reverse order. So it will go sum of squares 4, 4. And result here will be equal to 16. I'm just putting plus result here to demonstrate this. And then I'll go sum of squares here, 3, 4, plus results. And as a result here is going to be 16 plus 9, be 25. And then sum of squares 2, 4, plus results. The result here will be 25 plus 4, equals 29. So recursion goes down first with respect to your function calls, but when it's time to return each one of these functions and then to close them off, it goes in the opposite direction. So it'll go down first here from 2 to 4, and then it'll go in reverse from 4 back to 2, keeping track of the results here for each one of these return statements that we just had. And that's the reason why we need to keep on adding results here for our return statement. If we don't add results here, we don't keep track of our temporary memory variable that we created in order to keep storing the result for each one of those recursions. When I say each one of these recursions, remember, this here will be sum of squares 2 and 4 when we do our first function call. And then our second function call for sum of squares is going to be 3 or 4. And then for our next function call of sum of squares, it's going to be 4 or 4. And the only way that we stop doing these function calls for sum of square is when A goes more than B. And then it returns the results altogether. When it returns the results, it makes sure that we also end each one of these function calls here. And in order to do this, it starts with the most recent function call and it works backwards. So we'll go from sum of squares 4 or 4, get the results, sort as required. Then sum of squares 3 or 4, get the result for this sum of squares 3 and 4, and add it to the previous result that we had here. And that's the purpose of having add results here. So we get 16 plus 9 equals 25, and then the same thing happens here for 2 or 4, and we get 25 here being added to 4 with the square of 2, and that gives us 29. So that's how recursion works in this kind of case. Keep track of temporary memory. We saw earlier, once we didn't add that result, it was just not keeping track of the result variable as required for each one of those recursive functions. All right, so any particular questions regarding this recursion? No, you're not always required to have a temporary variable or a memoization variable. That depends on the situation that you're using. It does not depend on the approach. So like for instance, if we did the factorial code that we saw in yesterday's lecture, that didn't use any memoization at all. And that's because the factorial code doesn't need to keep a running track of some sort of temporary memory in order to get the results. So the only time when you use this temporary variable here, it is very dependent on the recursion situation. And a nice way to go about observing if you do need a temporary variable, which I did show you guys before, is that I didn't add it to begin with. And I checked to see if I got the correct results. And if I did not get the correct results, being that I got 0, that also meant that I also need to make sure that in that particular case, I did need a temporary variable to keep track of my recursion steps and to keep track of the results for each one of those function calls. So it is entirely situation dependent. And you will know once you start coding your functions recursively that once you start getting the wrong value being outputted, meaning like if you're getting 0 outputted or some other weird value, you are going to end up needing that temporary variable to keep track of your results accurately in order to get the correct value. Alright, it doesn't seem like we have any further questions regarding this. Let's move on to our last topic for today, which is going to be the black box approach with our A to I function. So I'm going to clean this up here. Let's get rid of this. And now we can get to this argc and argv thing. So remember from yesterday's lecture, argc basically keeps track of the count of the variables on the command line, and argv here stores the characters that are separated by spaces from the command line here. So let's say, for instance, that I wanted to have int add here, int a, int b. This is going to be my function on the test stack, and I'm just going to have return a plus b. And I'm expecting that my first input command line parameter is going to be a number, and my second input command line parameter is also going to be a number. So I can have int a here equal to 0, and then int b here is equal to 0. So I'm just initializing these as safety. And I can then say a is equal to a to I of argv1, and b here is equal to a to I of argv2. Now, a to I is a conversion function that transforms characters into numbers so long as those characters are numbers. And this in particular is that when you put a number on your command line, when using this sort of functionality here, that number is treated as a character and not an integer. So a to I here, a represents a character and I represents an integer. If we wanted a decimal number, we have used a to f instead to convert that character representation of a number into its decimal representation instead. So for now, I'm using a to I. And then I'll just put a cd out, add a comma b, end line. And I'm going to build my function here, build my program here. Now remember, because we're using command line parameters in our particular implementation, if I start without debugging, you're going to end up seeing that we're going to get some assertion fail here. It doesn't know how to handle this altogether, right? And that's because we didn't pass any command line parameters. So I'm just going to abort here and close off our program. So this means that we need to go to where our program has been built. So this will be inside your project folder. In my particular case, my project is named Sandbox. And I've built it in the x64 folder, my debug folder. And you can see here that I have a Sandbox application as required, and I'm going to have to copy this part, and I need to bring up a command prompt. Bring this up on my screen here, and I want to change my path here. So I'm going to put cd, and then I'm going to right click and paste my path that I just copied. Switch this to the path here, and I could just call sandbox, but I'm still going to get the same problem here because I didn't pass any command line parameters. Then I can say sandbox 1, 2, and you can see there is going to be add-in or variables as required. I can also say sandbox, let's say 4, 8, 4, 7, and I get my additions happening here as of such. And remember, this works because we're converting these characters here from the command line, being 4 and 7, from char data types into integer data types, a to I functionality here. Now, let's say if we want to do multiple additions without modifying our code here altogether, this is where the batch script comes in. So I'm going to leave this command line operating here because we're going to come back to it in a little bit. And I'm going to bring up a notepad file here. So bring up a new notepad file. And let's say I want to do multiple additions. So I'm going to be like sandbox 1, 2, sandbox 3, sandbox 411, sandbox 510, and so forth. The char is a pointer to a character representation of a number. Remember, all these numbers that we're seeing here from the command line, they're not number format, they're character format. How do I get the Notepad window? Just go here and the start menu and just type in Notepad. You'll just bring up the Notepad window. Same way, like if I go here and I type in command prompt, I'll just get the command prompt window here as well. So I'm going to be creating my batch script here to do multiple additions for us. So like 11, 20, and so forth. I can keep on going. And then I'll go File, Save As. I want to make sure that I'm in the same directory as where my executable program is. I want to switch this from text documents to all files. And I want to say, let's call this addition.bat. Now, we need to have .bat here to make sure that the file extension here is going to be of a batch type file. So that's why we give it a name first. So in my case, I say addition or add.bat. And this here will be our batch script. So I can minimize this and go back to my command prompt. I can call add.bat and it will run sandbox as required for us and produce our results that are required for each one of those additions. So yeah, another way to bring up your command prompts or your notepads is that you can do Windows key and R and you can type in CMD, or you can type in Notepad for the notepad and it'll also bring it up. But you can just use the start menu and you can just type in command prompt or notepad as required. So just to re-illustrate that, remember our addition function here. Sorry, our addition bat script here has multiple instances of sandbox being going. And for us to call this, we just call add.bat here, and it will run each one of these lines in sequence as if we're running a program. And it will just do this automatically for us and produce the results as required. So what would happen if I did not initialize A and B first? Let's see what happens. So it's A here, and it's B here. And let's call sandbox 2. It will still work as required. The only reason why I initialize these first here is just a matter of programming safety. Because if we don't initialize them, remember the compiler will do a random value initialization for variables. And most of the time, it assigns garbage. So it's a nice safety habit to make sure that you initialize your variables to some default value of your choice before you end up using them. Because in the event that you do end up using them later on and you forgot to initialize them, you don't end up getting garbage altogether later on. So that's a nice safety to do in particular. Alright, so I'm watching the time here and we're basically out of time for our tutorial. So if there are any further questions, feel free to leave them down in the comments below or directly email me. At this point in time, you guys are required to move over to the Blackboard Collaborate link for your session with Akash, requiring, I believe, the software engineering lectures or the computer systems lectures. Is either one of those two, but you need to be across there in the Blackboard Collaborate link at this point in time. So, like I said, if there are any further questions, feel free to leave them down in the comments below or directly email me. And next week, we'll be doing our lectures, in particular on the topic of space and time complexity, which is a very important topic regarding optimization of your programs. So until next week, take care, be safe, and I will see you guys soon. Later.